Hello, welcome to this first video in a series of videos that will describe simplifying non-variable radicals of higher degree. I'm going to attack this in a sort of four-prong approach here, and that will look like one, reviewing square roots, and we're going to be talking about simplifying square roots. And then number two is we're going to read and comprehend radicals of higher degree. And then we're going to look at understanding what to do when the radicand is negative. And a negative radicand, just for example, the radicand we talk about is the number under the radical sign. So in this case, if I wrote the square root of negative 33, the radicand would be negative 33. Just to fill in some vocab there, hopefully. And then we're going to do some examples. Okay, so let's jump right in here, and we are going to take a look at reviewing the simplification of square roots. Now, we've had two methods for this, what I've called the biggest square method and the 2-for-1 method. And I've got videos on this, and you should have great fluency in both of these methods by the time you get here. You want to go back and take a look at them if you don't. Okay, so the biggest square method involves understanding your squares. And your squares are numbers like 1, 4, 9, 16, etc., etc. And it relies on asking the question when you're going to simplify something like the square root of 48, what is the biggest perfect square factor of 48? And with a little bit of number sense, I realize that it's 16, so I rewrite this as the square root of 16 times this, 3. And then simplifying from there, I realize that I can simplify the square root of 16 and get 4. And I can't simplify the square root of 3, so I write the square root of 3, making the answer 4 times the square root of 3. Now this process, if you notice, it's just 2 steps, and it's a process that we want you to be good at. When you are simplifying square roots, it's really the preferred method because it's so quick. Okay. Now that being said, we want to recall that the 2-for-1 method revolves around making a factor tree. Okay, and then we're going to see what we mean by 2-for-1 when we do that. So 48, we're going to split into 2 and 24. And we're going to split 24 into 2 and 12, 12 into 2 and 6, and 6 into 2 and 3. And then by the 2-for-1 method, we use this kind of property here of the square root of a squared is equal to a. And this is because, if you notice, the 2 factors of a, when we do the square root, become 1 factor of a. So if we see that we have 2 factors of 2, we can rewrite it as 1 factor of 2 and create a product with that on this next 2 factors of 2. So what I'm doing is I'm pulling those out of the radicand in a 2-for-1 fashion. Again, these 2 became 1, these 2 became 1. And then I notice that left inside the radicand is a single 3. It has no pairs or partners, so I'll leave that inside the radical. Then this continuing to simplify the part that I can, I'll write the answers for root 3. We see very quickly that these answers are the same. Okay, so why do we have both these methods? Well, the biggest square method is very helpful, and it relies on a fluency of knowing your perfect squares, which you should. But when we get into higher degree, we would be talking about needing to know your perfect cubes and your perfect powers of 4 and your perfect powers of 5. And because exponents are involved, those numbers grow so quickly that they're not familiar to us. We don't really readily know those values. So we want to be able to put some focus on this 2-for-1 method. It's going to be, you're going to see that it's going to be an analogous method when we do things of higher degree. I'll give you a little hint now. When we do the third root of a number, we're going to do the 3-for-1 method. And when we do the 4th root, we're going to do the 4-for-1 method. And the 5th root we'll call for the 5-for-1 method. So we want you to know both methods, but this is the one we're going to continue to extend at this time. Okay, so let's move on from there and move over into reading and comprehending radicals of higher degree. So I have three examples here, and I'm going to talk about what these examples mean in terms of how they are read and what they stand for. This first one here is read the fourth root of 16. And what it means when we say it is what number times itself 4 times is 16. Okay? This next example is read the third root, or the cube root, of negative 125. And what that means is what number times itself 3 times is negative 125. And in this next example, where we have the sixth root of 4096, it simply means what number times itself 6 times is 4096. Well, with a little trial and error, you could probably figure these out. I'm just going to go to your calculator for a moment here and maybe do a little demonstration on how we can come up with these answers. So, square root is really simple, and you've seen your square root button, and it's just done by doing second square root of something like 9, and taking your right arrow out to close off the root, and getting 3. Again, I'm using a TI-84 Plus Silver Edition here, so it relies on the most upgraded operating system for you to emulate exactly what I'm doing here. The 83 Plus is similar. If you're smart enough to be here on this video, you might be smart enough to figure that out in terms of the subtle differences. So let's see what we have here. If I'm going to do the fourth root, I will in fact need to start with typing a 4. Now, I have to go to a menu here by hitting the Math button and seeing in my list down on number 5 that it says the xth root. Well, this allows me to take the fourth root, because I've already typed the 4. If you notice one line above, it's specifically the third root, but this one here on line 5 allows us to do any root, and we get in a higher degree. That degree can vary. So I'm going to now hit enter to pull that into my window, and notice that the 4 that I typed is now the index for the radicand. It's saying the fourth root of 16. And I will hit enter from there, and we see that it's 2. So the fourth root of 16 is 2, quite simply because what number times itself 4 times is 16? Well, that's the equivalent of saying 2 to the 4th and getting 16. Okay, similarly now, you'll notice that on problem 2, I'm going to do a cube root. Well, actually when I hit the math button, cube root's one of the options. So I see that number 4 is a cube root, so I'll just touch that. It brings the cube root into the command window here, and I'll type negative 125 for the radicand and hit enter. And we see that's negative 5. And this should make sense because of the simple fact that negative 5, and I'll put it in parentheses, to the third power is in fact negative 125. Okay, so just slide my calculator over here so you can see better. For this example of 3, again, I'm going to type the 6, hit math, choose number 5 out of my list, and see that the 6 turns into the 6th root of 4096, and the number times itself 6 times that gives 4096 is in fact 4. The reverse process of that is just doing 4 to the 6 and getting 4096. So, I hope this gives some understanding of how these radicals are read and what they mean, and a little bit of how to compute them on your calculator. So if you notice here, these all came out to be very nice answers. They were integer answers. We're going to be looking at what happens in problems that you don't get integer answers for. And that is going to cause us to use a simplifying algorithm like we did when we would do square roots that yielded not nice answers. For instance, if you were ever in a situation where you got the square root of 48 was a decimal, it would be an indicator that you should try and do the 2-for-1 method, or the biggest square method, and try and simplify the square root of 48. So we're going to apply that as we go into um, uh, radicals of higher degree as well. Okay, I'm going to break the video here, and we will queue up the next video from this four-part method that I'm doing, where we're going to try and work on understanding how to process a a radical of higher degree when the radicand is negative. So feel free to stop and make sure you go to the next appropriate video that connects to this and shows part 2 of the series.